So first of all, I'm pretty sure that you already know roughly how wireless networks are established today. So I have taken here a slide from Professor Gabriel Rebez, who is a professor at UC San Diego. And in fact, all of these slides are taken or adapted from his presentations. Essentially today what we do is we rely on what's called the sectored base station antenna system, which is the ones that you see right here. So each one of these antennas essentially cover a fairly wide range of space. It could be 120 degrees, which is most common, or roughly 90 degrees in some other cases. But the whole idea is that I don't need to know where you are. Your cell phone has practically an omnidirectional antenna. So no matter where your cell phone are, no matter where you might be, you will be receiving a signal from these systems. So that essentially is what we call the broadcast model. So we have one main base station. Of course, there are many of those in real systems. But we have these base stations that cover specific cells. And so far, nobody really wonders about how do you locate where you are. However, if you want to significantly improve your bandwidth and data rate, then you have to go in this idea of directive communication. Essentially, we have to move closer to the paradigm of point-to-point communication instead of a broadcast model. So let's see why that is. So I've actually plotted here an interesting scenario based on the Friis transmission formula we've seen in this class, where what you will see here on the vertical axis is the power received, and the horizontal axis is distance. And I'm using, again, the very simple ideal model, the Friis transmission equation, and some realistic or semi-realistic assumptions. So I'm assuming that the transmitted power here is basically 1 watt. I'm assuming that the gain of the base station is about 10 dB. I would say that's a pretty reasonable assumption for many base stations out there. And I'm assuming that the gain of the receiver antenna, which is the gain of my cell phone, is about 0 dB. And in real life, by the way, receiver antennas in cell phones have gains well below 0 dB. 0 dB actually is a pretty forgiving assumption in that case. A lot of times you will see gains in cell phones down to the 6 dB, 7 dB, negative, I mean, -6, -7, and so on. But anyways, nevertheless, let's assume it's about 0 dB. And then I'm assuming that I need to receive roughly a 16 QAM modulation scheme, which we did cover in this class. And for that one, for a 1 gigabps data rate, I need to receive roughly -65 dBm. So if you look into the Friis transmission equation, you will find out that roughly speaking, if you're operating in one of these bands, 30 or 60 gigahertz, which are 2 of the millimeter wave bands that 5G will exist on, you're basically covering distances in the order of 10 to 100 meters if you must maintain a -60 dBm power range. So as you can see, the distance, once you move to millimeter wave, basically drops dramatically. Today we can cover miles. There we're basically limited to 10 to 100 meters. And again, the situation is for the simple model, the 1 over d square. By the time you go to multipath communication or other obstacles, that model basically fails. But let's see what happens when we start putting gain in the system. Something amazing happens, and most people actually don't realize how important that is. So now let's assume that my gain in the transmitter base station is now 33 dB. For those who may not be familiar with a 33 dB, that is a gain of 2,000. It's quite a bit. And you can actually get this type of gain with this type of an antenna array. So it's not unreasonable to get this type of a gain. And we will cover back a little bit of the basics of antenna arrays if you're not familiar with those. And that corresponds roughly to a 6 degrees beam width. Now, if you have also an antenna array on the cell phone side, let's say roughly a 4x4 antenna array system, that will give you about 26 degrees beam width. And when you take and you multiply those, now you can see that your range starts becoming in the order of kilometers or more. So again, this is not to say that with these parameters you will gain a gain of a kilometer, because the propagation model is completely unrealistic. But it is to say that if you can actually increase your gain with transmitting basically the same power, you can increase distances by at least an order of magnitude, probably more. And that concept is the key concept that actually makes 5G in millimeter waves actually practical. Now, you might say, is it for free? Well, it's not for free. We're going to discuss actually what technological advancements had to be made to make this thing a reality. But before we talk about technology, what you need to realize is that there is a huge penalty in doing this. And the huge penalty in doing this is the need to know where the receiver is. So I have to align by beams clearly in the transmitter and receiver for this concept to work. And before we were able to make antenna arrays inexpensively, the only way we were able to do that is by literally mechanically moving an aperture, which is not very interesting. And with antenna arrays, on the other hand, as you're moving, I can relocate the beam to basically hit you in the order of nanoseconds or microseconds. And not only this, but I can actually have independent beams for different users. So beam forming approaches are basically very advanced today, and that's why this concept actually works. Now, let's talk a little bit about antenna arrays, because I understand that some of you may not have covered these things in the past. So what is essentially an antenna array? It's a very, very old concept. It's probably close to 100 years old right now. And it basically has this very simple idea that if I can basically put antennas right next to each other, so here's antenna 1, here's antenna 2, here's antenna 3, and so on. These antennas are shown here as patch antennas, but they can actually be any type of antennas. If you can actually put these antennas together, and if you can basically control the phase that you're feeding these antennas with, essentially you can coherently add the signals that they're getting back. And so it's that simple of an idea. And so when you can basically coherently add the signals, you can start gaining essentially a very sharp beam width, which is much sharper than each antenna would give you by itself. So what you need to make this thing is you need to include phase shifters. And so these phase shifters are shown essentially schematically right here that essentially control the phase of each antenna element. And that's true both for transmit and receive. The other interesting thing is not only you result in nice sharp beams, but you can actually do electronic scanning. That's the huge advantage compared to mechanical antennas, is the fact that I can digitally control what these phases are, and that means I can decide to change the direction of the main beam in the order of nanoseconds or microseconds, depending on my technology. So if you basically think about that, since you're doing essentially spatial power combining, you're getting a directivity in the order of n. N is the number of elements. And so that means that if you're a receiver now, and since you're adding now the signals coherently, but the noise is not added coherently clearly because it's uncorrelated, at least to a first degree of approximation, that means that you're actually improving in the receiver side your signal to noise ratio by n in dBs. Now that's on the receiver side. If you have an antenna array on the transmitter side, things are actually even better because your transmitter actually now radiates a lot more power. Since you have n antennas, you radiate n amount of power compared to each antenna. And you have the gain, which is basically also added because you have the gain of the antenna array. So basically, you gain an n square here. And so that essentially means that if you take the total system, transmitter and receiver, you're improving things by an amazing n to the cube. However, we need to be aware that this is only true if you're comparing the system to a single element, and as I was basically doing before. If you're comparing the system to a mechanical aperture, like the dishes that we discussed before, the satellite dishes, essentially you're getting nothing. You're getting no free lunch. Essentially, the only advantage you have compared to a reflector beam is the fact that you can do electronic steering. But other than that, your system improvement is the same. You do have a penalty to pay for this ability to do electronic steering, and that is the fact that, as we're going to see in a couple of examples later on, your gain actually drops as you're scanning your beam. So it's common to have plus or minus, let's say, 50-degree scanning, and at the edges of that scanning, your gain will be lower. This is simply a fact of antenna arrays. Your antenna impedance changes as you're scanning, and that's another huge advantage. That as you're changing basically those phase shifters, the mutual coupling between antennas actually does change, which basically means that it's harder to feed these antennas with a constant matching. But nevertheless, all of these design challenges are essentially can be met, and that means you can essentially make a system, as we're going to see in the next video, that basically allows you to make an amazing communication system.